Now we introduced measurements in level 1. We saw measurements for length, mass, volume and capacity. In this section we go further and look at length, measuring length and particularly small length in the scales of millimeters and even smaller. You recall that the SI unit for measuring length is meter, but we also saw the various multiples and submultiples of a meter. And this is very important. Why? Because the range of measurement is quite large, from way bigger than kilometers to way smaller than millimeters. So if I have the SI unit for length, that is meter here, the submultiple is 10 raised to power 0. Remember, any number raised to the power of 0 is 1. The tenth of a meter is decimeter, the hundredth is centimeter, all the way to billionth, which is called a nanometer. The billionth of a meter is called a nanometer, that is 10 raised to power negative 9. Upwards, 10 meters make a decameter, 100 meters is hectometer, up to gigameter, which is a billion meters. 1 billion meters, that is 10 raised to power 9, is equal to a gigameter. But in most cases in physics, measurements will range from millimeters to kilometers, which is a comfortable range. In this section, we shall look at measuring small distances using two instruments, the micrometer screw gauge and a vernier caliper. Actually, it is the main focus of this chapter. So let's get right into it, and we start with the micrometer screw gauge. A micrometer screw gauge is an instrument used to measure the thickness of a wire or thickness of sheets of metal up to an accuracy of the third decimal place of a centimeter or a hundredth of a millimeter. It has a U-shaped frame with a flat end called the stud or anvil. There is a cylindrical nut at the end which is threaded from inside. There is a screw with a flat end that can move inside the nut by rotating a hollow cylinder or thimble provided at the other end. A reference line graduated in millimeters is drawn on the cylinder or sleeve attached to the nut. This is the main scale. The hollow cylinder or thimble is also graduated and is divided into equal parts, generally 50 or 100 parts. This graduated part of the hollow cylinder is known as the head scale or the circular scale. There is a ratchet attached to the screw. The ratchet is used to turn the screw. The object whose thickness is to be measured is placed between the anvil and the flat end of the screw. Whenever you want to use the screw gauge, you must find out something called the pitch of the screw. The pitch is the distance moved by the tip of the screw when the head of the screw is rotated once. That is, the pitch is the distance between two consecutive threads on it. In order to determine the pitch, rotate the screw, say 5 times. Record the distance moved by the main scale. In my gauge, the distance moved is 5 millimeters. Number of rotations is equal to 5. Pitch is the distance moved by the thimble on the main scale divided by the number of rotations, which is equal to 5 over 5, which gives me 1 millimeter. Next is the least count of a screw gauge. This is the smallest distance moved by the tip of the screw when the screw turns through one division. Least count is equal to pitch over the number of divisions on the circular scale. So in my case, this is equal to 1 over 100, which is equal to 0.01 millimeters. This is the accuracy of my screw gauge. And then again, we have determination of zero error. Sometimes on bringing the flat end of the screw in contact with the anvil, the zero of the circular scale does not coincide with the zero of the main scale. This is a mechanical error and is called the zero error of the screw gauge. Depending on the position of the zero of the circular scale, the zero error can be positive or negative. On your screen are three screw gauges. In A, the zero of the circular and that of the main scale coincide. This screw gauge has no zero error. In B, the zero of the circular scale is below the reference line of the main scale. This screw gauge is having a positive zero error. Let's find the zero error. Note the division of the circular scale that coincides with the reference line of the main scale. Zero error is equal to coinciding circular scale division times least count of the screw gauge. In my case, this is equal to 2 times 0.01, which gives me plus 0.02 millimeters. For screw gauge C, the zero of the head scale is above the reference line of the main scale. It has a negative error. To calculate the negative zero error, note the division of the head scale coinciding with the reference line of the main scale. Also, note the number of divisions on the head scale deviating from the reference line of the main scale. In this case, it is 2 divisions. Multiply this by the least count. That is 2 times 0.01, which gives me negative 0.02 millimeters. Having known the least count and calculating the zero error, if present, you can now calculate the thickness of a sample using the formula observed reading is equal to main scale reading plus coinciding circular scale division times least count. And then the true reading is equal to observed reading minus plus or minus the zero error. Now for the screw gauge on your screen, it is free of zero error. So let's use it to determine the diameter of a wire. So we place the wire between the anvil and the flat end of the screw. Turn the ratchet clockwise to hold the wire gently. Now I can take my readings. Main scale reading is 3 millimeters. Coinciding circular scale reading is 55. Then calculating 3 plus 55 times 0.01, I get 3.55 millimeters. No zero error, so this is also my true reading. I can repeat the experiment for various sections of the wire. Again, the main scale reading is 3 millimeters. This time coinciding scale reading is 53. Calculating 3 plus 53 times 0.01 gives me 3.53 millimeters. So if I have such a micrometer screw gauge on your screen, what I have here is an object we are going to measure. I put the object on the screw gauge and now close the screw gauge till I get a firm grip. Alright. Now I'm going to try to read the measurement. You notice on the screw gauge the main scale on the sleeve is yellow and the circular scale is green. On the main scale on the sleeve we have divisions on the top and below. The top scale represents 1 millimeter each, whereas the bottom indicate halfway between 1 millimeter, that is 0.5 millimeters. So if I'm reading, I shall have 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, and 5.5. So I record 5.5 millimeters. Moving to the circular scale, the coinciding mark with the reference line of the main scale is 21. So I multiply by the least count and add to the main scale reading. So I shall have 5.5 plus 21 times 0.01, and if I finish that I get 7.71 millimeters. So the thickness of this block is 7.71 millimeters. Excellent.
Next, we look at vernier calipers. Vernier calipers is used to measure the length, thickness, diameter and depth of an object and to measure the internal and external diameters of a hollow cylinder. It is also known as a slide calipers. It can measure up to an accuracy of 0.1 millimeters. The two scales you see on the vernier calipers are the main scale and the vernier scale. The main scale is a long thin steel strip with jaw J1 at one end and is graduated in millimeters. The vernier scale is a graduated movable steel strip with jaw J2 that can slide over the main scale. Generally, the vernier scale has 10 divisions marked on it. The vernier scale can be fixed at any position on the main scale with the help of a screw. The jaws J1 and J2 are parallel and projected on either side of the main scale. The lower jaws are called the outside jaws. They are generally used to measure the length or the thickness of a given rod or diameter of a given sphere or cylinder. The upper jaws are inside jaws and are used to measure the internal diameter of a hollow cylinder or pipe. There's a thin long strip T attached to the vernier strip at the back of the main scale. This is used to measure the internal depth of cylinders or hollow tubes. The object to be measured is placed in between the lower or outside jaws. Whenever we use vernier calipers, we have to first find the least count and the zero errors of the instrument. Least count is the smallest measurement that an instrument can accurately measure. To know the smallest measurement, we must first know the number of divisions on the vernier scale and the value of one main scale division. For these calipers, number of divisions on the vernier scale is 10. Value of one main scale division is 1 millimeter. Least count is equal to the value of one main scale division over the total number of divisions on the vernier scale. That is 1 millimeter over 10, giving us 0.1 millimeters or 0.01 centimeters. Zero error. It is found that at times, when the movable jaw is brought in contact with the fixed jaw, the zero of the main scale does not coincide with the zero reading of the vernier scale. This is a mechanical error and it's called the zero error of the vernier calipers. Depending on the position of the zero of the vernier scale, zero error can be positive or negative. Here are three vernier calipers, A, B, and C. In A, the zero of the vernier scale and that of the main scale coincide. That is, vernier calipers A is free of any zero error. In B, the zero of the vernier scale is to the right of the zero of the main scale. This calipers has a positive zero error. Let's find that error. Note the vernier scale division that coincides with any division of the main scale. To get the zero error, multiply the coinciding vernier scale division by the least count of the vernier calipers. The vernier caliper C is having a negative zero error because the zero mark of the vernier scale is to the left of the zero of the main scale. To find the zero error, first note the division of the vernier scale that coincides with any division on the main scale. Subtract the coinciding division from the number of divisions on the vernier scale. Multiply the difference by the least count and assign it a negative sign. After finding the least count and the zero error of the vernier calipers, we calculate the observed reading using the formula. Observed reading is equal to main scale reading plus the vernier scale division times the least count. True reading is equal to the observed reading minus plus or minus zero error. For example, let's determine the length of this rod. First, we find the least count. Number of divisions on the vernier scale is 10. Value of one main scale division is 1 millimeter. Least count is equal to 1 over 10, which is 0.1 millimeters or 0.01 centimeters. Then we check whether it has a zero error. It does have a positive zero error. Coinciding vernier scale division is 6. Zero error is equal to 6 times 0.01, and that is equal to plus 0.06 centimeters. We fix the rod between jaws J1 and J2. Main scale reading is 4.6. Coinciding vernier scale division is 3. Calculating.
So next, let's get a bit mathematical and look at significant figures. Now, sometimes and in many instances when we do calculations, our computations give answers with very many digits. Look at this example on your screen. Now, I don't know which instrument can give a measurement to this accuracy and how necessary that will be. We therefore express numbers in simple forms using only the significant figures correct to the desired degree of accuracy. The rules governing significant figures include: first, significant figures are counted from left to right, very important. Secondly, all non-zero digits are significant. 0 may or may not be significant depending on its position. If a 0 occurs in between non-zero digits, then it is significant. For example, 7052, 7.204, both have 4 significant figures. The zeros are significant because they are occurring in between non-zero digits. If the 0 occurs at the right end after a decimal, it is also significant. That is like 5.0 has 2 significant figures, that 0 is significant. 2.00 has 3 significant figures. Now, when a 0 occurs at the left end of a number, it is not significant. Now, here is where the problem comes. If a 0 occurs at the right end of an integer, it may or may not be significant. For example, look at the number 760,000. It could be correct to 2, 3, 4, 5, or even 6 significant figures. When the number is expressed to two significant figures, none of the zeros is significant. So we'll still have 760,000. You realize you cannot take 76 because you ultimately have changed the number. So in that case, correct to two significant figures, we will retain the number 760,000. But then in that case, all the zeros will not be significant. Now, conversely, to 6 significant figures, all the zeros are significant. Interesting. So if you want to correct to 3 significant figures, the last 3 zeros will not be significant. If you correct to 4 significant figures, the last 2 zeros will not be significant. Of course, to 5 significant figures, the last 0 will not be significant. Now let's say I want to correct that number to 1 significant figure. Now I count from the left, the first digit is 7, so the digit right after it is 6. 6 is bigger than 5, so I make it 0 and add 1 to 7, so I shall have 800,000. 800,000 correct to 1 significant figure. It means all the zeros are non-significant. Well, as you think about that, let's move to the next item, that is standard forms. Again, sometimes when we write numbers, they are either too small or too large. Look at these numbers on your screen. Writing these numbers takes a lot of space and consumes a lot of time. Of course, not to mention that they are tedious to read and write. So we write them in standard form. Numbers in standard form are written in the form a times 10 raised to power n, where a ranges between 1 and 10, but 10 is excluded. Now you can see that from that inequality, n is an integer, that is all whole numbers, positive and negative, and 0 included. When any number is raised to 0, it is equal to 1. For example, 10 raised to power 0 is equal to 1, 5 raised to power 0 is 1, x raised to power 0 is also 1. So for any number like 228, we can write it as 228 times 10 raised to power 0. That 10 raised to power 0 is 1, so the number doesn't change. But in standard form, a must never be 10 or more. So we move the decimal point 2 places to the left to make the number 2.28. Now that lies between 1 and 10. When the decimal moves to the left, the power of 10 increases equal to the number of places the decimal moves. So we shall have 2.28 times 10 to power 2. The decimal moved 2 places to the left. If the decimal moves to the right, the power of 10 reduces by the same magnitude. Of course, you expect that to be the case. If we have 0.00429, we can have it as 0.00429 times 10 raised to power 0. Again, 10 raised to power 0 is 1, so it doesn't change the number. But a has to lie between 1 and 10. So our decimal moves 3 places to the right till we get to 4.29. 4.29 lies between 1 and 10. The power decreases by 3, giving us 4.29 times 10 to power negative 3. It's that simple.
In this modern time, the 21st century, we tend to take for granted a great deal of the technology that we are faced with today. The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room, and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment as Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course, this was electrical energy. Now, you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cuneus at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful, and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.